Today it's my pleasure to deliver a talk about quantization support for ONNX using Intel low precision optimization tool. The work is closely collaborates with Shrub and many other colleagues. As you may know, low precision is gaining more attention and is being adopted in various domains in the industry. So to support the rapid growth of low precision solution, we created an Intel low precision optimization tool helping Intel customers deploy low precision solution, either for deep learning frameworks on both CPU and GPU. The supported mixed precisions are int8, BF16, and FP32. And the verified hardwares are all the generation of Xeon scalable processors from Skylake to upcoming Ice Lake and Sapphire Rabbit, and also the Intel Xe architecture-based GPU. You can see the right top diagram showing the output architecture. The top is the FP32 model as the input. The middle is the output, including auto tuner as the user-facing APIs, and the other key components like quantizer, pruner, benchmarker, and tuning strategy. And also the frame adaptation, including ONNX runtime adapter and the other frame adapters. Now let's look at the simple usage flow and the code example at the left bottom side. Given the FP32 model as the input, user just need to prepare a configure as shown below and launch output with minimal lines of code change. The configure is template based, so user just need to take the template and update some minimal item. For example, the quantization approach, here we use the post-training static quantization, and the quantization dataset. Launch code is also pretty simple. 4 lines of Python code created from the configure and do quantization, and then save the quantized model. Then you can see the right bottom diagram showing the auto tuning flow. Given the configure with accuracy criteria and the timeout, output will generate a quantized model with the quantization configure driven by the tuning strategy. Once the accuracy is meeting the criteria or the other objectives meet the criteria or is reaching the tuning timeout, the tuning flow will stop with the best quantized model with the trade-off of the accuracy and the other objectives. Now we want to show the quantization productivity with output, reducing the time from days to minutes, showing the significant productivity improvement. Compared with human expert, you will see output is helping in all those 3 key aspects for quantization, including effective model calibration, advanced quantization recipes, and the systematic auto tuning flow. Effective model calibration saves the efforts to collect the tensor statistics from the scratch, and advanced quantization recipe help reaching the higher accuracy and shorten the tuning space. And the systematic auto tuning flow, as described in previous page, is greatly releasing the manual effort to tune the accuracy per quantization recipe. Generally, for a big model, for example, REST50, there are 53 convolutions. Then people need to tune per layer for those quantization recipe, which is a very huge space. So overall, we expect the output will improve up to 90 quantization productivity improvement, and we already received very positive feedback from our customer and in the real use case. Below is the table to show the model using output compared with the FP32 baseline. The models cover the typical workloads like REST50, VGG, computer vision, and the various BERT and BERT variant models. You can see the accuracy is kept within 1% loss, and the tuning time is less than the 40 minutes, and for those BERT model actually it's just like 1 minute. We expect to improve the productivity further with the more advanced tuning strategy or the quantization recipes, as well as the more optimal quantized kernel from ONNX runtime. And the latest output release supports the two quantized OP categories. One is the Q linear ops, the other one is the integer ops. And we notice the latest ONNX runtime as more quantized operators supporting the 1.7 release, and output will also include them in the next release. Meanwhile, output supports two quantization approaches, which is the static quantization and dynamic quantization. Static quantization is mainly for the computer vision workloads, for example, Red 50, VGG, and the dynamic quantization is mainly for the NLP models for BERT and the other transformer models. Now let's talk about the release collaborations and the plans. Airport v1.2 will support the ONNX runtime 1.6 with the offset and operator-wise quantization tuning. And the later release 1.3 will support ONNX runtime 1.7 with the new quantized operators. And Output 1.4 will integrate the Python optimizer tool introduced by the ONNX runtime 1.7 and support the more flexible graph transformation for NLP models. On community collaborations, we welcome the contribution from the community to improve output together. So please submit a pull request on the new features and find an issue in case some is not working as expected. Just take a look at the contribute guideline on the Airport GitHub. So in the future, we plan to continue improve the output and contribute the quantized model to ONNX Model Zoo and enrich our product release distributions channel. For example, we will release a Docker binary and also the Niter build binary to the community. Well, this is the end of my presentation. Thank you very much for your time.